Hi, my name is John Ballato, and I'm a professor of material science and engineering at Clemson University. I also direct a center at Clemson called the Center for Optical Materials Science and Engineering Technologies, COMSET, and I was asked to provide this brief video introduction to a paper of ours that appears as the feature article in the September issue, which looks like this, of the Journal of the American Ceramic Society. The paper is entitled, as I think you can read, Rethinking Optical Fiber, New Demands, Old Glasses. And I'm one of the co-authors, and the other co-author is Dr. Pete Dragic from the University of Illinois. Say hi, Pete. Hi, Pete. The premise of the feature article, which we're going to talk briefly about today, is that optical fiber, which many of you have heard of, but probably don't really understand either how it works, what it does, or what it really enables. So maybe that's the best place to start. So the use of light was recently, there we go, highlighted in a National Academy study that came out this year, 2013. And that application of light annually, globally, is about a $7.5 trillion business. So the use of light globally as a market is about half the GDP of the entire United States. So it is a humongous market. This was just the summary. This is the actual report, all 300 pages of it. Anyway, that global market enables pretty much everything that you think about when it comes to communications today. All of that information routed around cell phone, data, video, goes at some point on its path around the world through an optical fiber. Lasers are used for cutting and welding and all sorts of other things. Technically, you're viewing this on the screen, so I'm not shining you in the eye with a laser beam, but nonetheless, the use of light, again, $7.5 trillion. A growing amount of that is actually being carried by optical fiber, and that is, again, the focus of this paper. Optical fiber, which looks like this, actually, this is optical fiber that we made here at Clemson. It's a hair-thin strand of glass, and when I say hair-thin, it's hair-thin. It's about the size of your hair. Your hair is about 100 microns. A conventional telecommunications grade fiber, like this is about 125 microns, so about the same, more or less, in diameter, but remarkably strong. And it's made of beach sand, silica, SiO2. The premise of the paper that appears in this September issue that we're talking about briefly is that optical fibers enable a considerable fraction of that global optics business. Optical fibers from a materials perspective, however, are remarkably boring. So by and large, they're made of, again, silica with some few percent of an additional dopant in it to change the optical properties so that the fiber itself can actually carry, confine, guide the light from one point to another. There's nothing wrong necessarily with doing things the same way for a very, very long time. However, the problem is today that you all, the consumer, are placing so many demands on light, whether it's downloading video on demand, downloading video, streaming videos, email, data, texts. All of those things are forcing much, much more light over the existing networks. And other applications such as military, defense, security, biomedicine, cutting, welding, manufacturing, things along those lines. The greater and greater use of lasers has also forced the materials that go into them to have to be rethought. So many of these optical technologies that you enjoy and benefit from every day are based on materials that were really invented or really brought to commercial reality, in some cases 20, 30, maybe even as many as 40 years ago. And they have worked extraordinarily well. You wouldn't have datacom as you have it. You wouldn't have the internet as you know it today, or any communications for that matter. And you wouldn't have cars and planes and many of your modern conveniences today if not for the use of light. But again, the materials that are really doing all the work behind the scenes. The glass in the fiber, the crystals in the laser themselves, things like that are, again, things that worked a long time ago. They solved the problems that that industry had years ago, but they're not necessarily up to the task today. And so what we find ourselves faced with is, remember this, periodic table. So this is the spice rack that material scientists like me and my colleagues here at Clemson and others within the Glass and Optical Materials Division of the American Ceramic Society, that is what we use every day. So someone will come to us and say, we have a need, in this case for the use of light. What materials or combinations of materials can you put together so that when the light comes in and then the light goes through the material and then it comes out the other end, the material has transformed the light in some way? The problem, if we focus on fiber for a minute, the problem is, given the 100+ elements on that periodic table and the millions and millions and millions and millions of permutations of combinations of those hundreds of atoms, at the end of the day, I hope you can see this, at the end of the day, only a few of those elements are actually used, right? So the glass is mostly silica, SiO2, those are the two red squares. And then to make the core slightly different materially so that it can confine the light, we'll add in elements like fluorine, maybe, boron, aluminum, phosphorus, germanium. And that will go into the glass network. It'll change the properties of the glass, and it'll have the light do something a little bit differently. Okay. But again, we are going from this remarkable thing called the periodic table and all the possibilities that those elements present in terms of new materials. And we have little by little shrunken down the periodic table to this, important but really much, much smaller subset of glass compositions that can be used. So we find ourselves today in a conundrum where the demand for light, and particularly light that is going over a fiber, has taken us to a point where the glass from which the fibers are made aren't keeping up with the demand. So what winds up happening is the light comes in, the glass, in response to the power or the intensity, the brightness, the energy of that light, responds in a way that we don't want. So nonlinearities come up, Raman scattering, Brillouin scattering, things along those lines. Effects that are nominally very, very weak, but again, as the power of the light going through the fiber has gotten higher and higher and higher, even small and very weak effects begin to add up, and those effects then ultimately deteriorate the system in one variety of ways. And so the long of the short of that is that the fibers are unable, or will soon become unable, to keep up with the performance demands that the consumer is placing on the networks in which the light is being carried. So there are a couple of approaches to that. One is, well, you develop a new material. If material A isn't working, well, let's develop material B. The other, which is oftentimes what is done, but in the case of optical fiber, there is something of a different trajectory that has been taken place. So instead of developing a new material, what the optical fiber community has done really over the last maybe 10 years has played a game that material scientists by and large invented, which is structure property. So to influence the behavior of something, you can either change its material, or you can change its structure or its microstructure. Both of those have an effect. And so what you find is that optical fibers, or many of the high performance fibers these days, look like this in cross section. They are combinations, periodic combinations of holes and solid regions that can really do a remarkable job controlling the properties of light as it propagates through the fiber. The difficulty, these are, and as you can tell from looking at them, they are extremely difficult structures to make. And so the solution to making optical fibers perform better is complexity, is to go to a structure that is more complex than the previous generation of structures. And at least in my book, or mine and Pete's book, or our feature article more precisely, complexity is rarely a solution to anything, right? Nature abhors gradients. Nature abhors complexity. It tends to move in a direction that favors simplicity, right? And so much of the paper is dedicated to essentially saying, while this is very great science that has come out of this, complexity is not necessarily the solution. What we are advocating for in the paper is that instead we go back to the more conventional approach, which is let's develop new materials. Problem with oftentimes developing a new material is new materials are oftentimes considered exotic. And what that means is they're expensive, or they don't perform well enough, or it's great for academic research, but transitioning the technology to industry and to larger scale manufacturing, as is required for something as high volume as optical fiber is, there are inherent difficulties in that, which is why at the end of the day, after decades and decades and decades, we're still using materials like silicon, silica, YAG, sapphire, things like that. So if you look at the use of materials in optics, at the end of the day, there are only 3, 4, 5 materials that really do the lion's share of all the work. And again, from a materials perspective, that's extraordinarily boring and extraordinarily limiting in what can be done. So what we talk about in this paper is reinventing, rethinking optical fiber, but purposely, though, realizing that it's got to be done in a way that's still manufacturable, scalable, and amenable to existing processing. So if you're going to reinvent, you want to just reinvent the wheel, and you have to reinvent the entire process to make the wheel. Neither of those two things are useful in terms of actually maturing and implementing a technology. So we don't want to get rid of the present fibers. We just want to rethink the way that they're made, but still done in a way that can be fit into existing processes. So the way fibers, the vast majority of commercially available fibers are made is through a chemical vapor deposition process. And so things like silicon tetrachloride, germanium tetrachloride are flowed onto, through a tube, or oftentimes a tube of silica glass, and reacted at high temperatures with oxygen to give you the silica SiO2 glass, which may or may not be doped with some of these other things like germanium to control its optical properties. That process, or the processes along those same chemical lines, were developed in the 60s and 70s, and they worked extraordinarily well, which is why you have this information technology revolution that you do today. However, in the chemical process for making those glasses, and then the thermal process by which the glass is actually heated up and ultimately drawn into fiber, in the combination of chemistry and temperature and time that go into converting those gases ultimately into a rod of glass, ultimately then into a fiber, the combination again of chemistry, time, and temperature is part and parcel of what actually limits your availability of elements on the periodic table. And so what winds up happening in many cases is that compositions of glasses that could be quite extraordinary from a performance perspective don't survive the combination of, again, composition, temperature, and time that the processing imposes onto the choice of materials. And so one thing that oftentimes will happen is phase separation. And so just like oil and water, certain compounds like silica and, for example, alumina, so sand and sapphire, very common materials individually. If you mix them in reasonable proportions, then at high temperatures, above where they both melt, they are immiscible. Oil and water, they will separate out either at high temperatures or even in some cases at lower temperatures. There's a solid immiscibility in that particular system. There are other systems like barium oxide or the alkaline earth oxides and silica that have liquid immiscibilities. The point is, if you want to make a new glass that has a reasonable amount, say 15 or higher % of alumina in silica, or barium oxide, or any of the alkaline earths in oxides in silica, you can't do it given the time and temperature that the chemical vapor deposition processes employ. They will phase separate either in liquid or solid phases, and you will get something again that doesn't transmit light, which tends to negate its use as an optical fiber. So essentially the fibers, the choice of elements from the periodic table that are available for the use of fibers is not so much based on whether the materials themselves or what the materials do to light. It is more dependent upon how they impact the process, or how the process impacts them, and can you actually make them into glass. And so what we realized is, again, you're throwing away the vast majority of the periodic table. There's no need for that. You're being thrown away because of the choice of process that we employ. And so part of our advocacy for rethinking this is rethinking again how these fibers are made. And so in the paper it talks at great length about what is called the molten core process. Molten core process was something that we invented at Rutgers, my alma mater, which I think you can actually see behind me there. For making fibers directly from compositions that, again, were nominally unstable. You couldn't make the glass and then draw the glass into fiber directly, because there was something that would happen. It would crystallize, the glass would crystallize, it would phase separate something. And so the molten core process is a very simple concept. You take, as oftentimes you do when you want to melt something, you put it inside of a crucible. You put the powder inside of a crucible, you heat it up, you heat it above its liquid as it melts. Then you have a liquid, and if you cool that quickly enough, if you again quickly enough so that you don't either phase separate or induce crystallization, you can kinetically hinder those things and get a homogeneous glass. But we take a little twist on that, and instead of a crucible, or as the crucible, we actually use the silica cladding that ultimately becomes the fiber. And the core is essentially the melt. So in practice, what one does is you take a tube of silica, which you're going to draw at about 2,000 degrees, which exceeds the melting point of a great many materials anyway. Take a tube of silica, close off one end, seal off one end, essentially acting as a crucible, and into that tube you sleeve a compound that is going to melt at a temperature below where that glass draws into fiber. So as that silica cladding is drawing into fiber, the core is melted. It's molten, which is normally not the case when you're making fiber. That molten core then, as the fiber is drawn and the fiber cools, that melt solidifies. And again, if you do this right and you do it quickly enough, you get an amorphous glassy core phase, which is what you want for the light to propagate with reasonably low loss. And so by processing it up above the liquidus, or sufficiently above the liquidus, you can mitigate some of these immiscibility issues or phase separation issues that plague, again, a wide variety of materials that you would like to use but couldn't based on the periodic table and their interactive chemistries. But what we found is a little bit more than that. So it is also known that whenever you take something and you melt it inside of a crucible, there's always a little bit of chemical attack between the melt and its crucible. There's always a little corrosion or dissolution of the crucible by the melt. Sometimes that's good, but it's usually bad. In this case, you can start with, again, whatever the core phase is that melts when the cladding is drawing into fiber. But that melt attacks, dissolves some of that cladding silica, and it brings into that melt some silica. That actually is of benefit because the silica can help facilitate the formation of the glass. It makes it in many ways compatible, or more compatible, with the cladding itself, and it also is a way to tune the optical properties. And so you have some additional benefits of this corrosion, or this dissolution of the cladding glass by the core melt as it is being made into fiber. So again, in this case, you're not making a preform and drawing it into fiber as you typically do. So you're removing an entire unit operation out of the processing. You simply have a tube sealed, sleeved into its center is a phase that will melt at the draw temperature, which then interacts with that cladding glass to form actually a different composition than the one that you start with. And it goes directly into the fiber at the end. So let me give you a few examples that we talk about in this paper. One example is actually silica clad and sapphire core. And again, sapphire is well, one thinks about it with respect to gemstones and things along those lines, but industrial sapphire is very, very common and really quite cheap. So if you put sapphire inside of a rod of sapphire inside of a tube of silica, you have to go a little hotter than you would normally go because sapphire melts at about 2050 centigrade, so you have to draw a little hotter than usual. But nonetheless, you can melt the sapphire. As the sapphire melts, as the aluminum melts, it attacks a little bit of that silica and dissolves the silica in. As the fiber draws and it cools, that melt solidifies, and you wind up getting a silica-clad fiber with a high alumina content, aluminosilicate glass core. What is particularly interesting, other than the fact that that composition is again one that is normally very, very difficult, if not impossible, to make under practical conditions. What is particularly interesting is that silica has a positive photoelasticity, which means as when you squeeze it, its interaction with light, there's a certain direction that the refractive index changes in a positive way. Alumina has a negative photoelasticity, so when you squeeze on it, the change in index in response to that squeeze goes in the opposite direction, goes negative. And so it stands to reason that if you take a material that has a positive effect and a material that has a negative effect, and you mix them together, then there's a composition where those effects cancel out. And so you conceivably could have a fiber, or would have a fiber, that has zero photoelasticity. And while that may sound interesting, academically curious, it's practical in one particular way, which is that Brouin scattering, which happens to be a nonlinearity that, or stimulated Brouin scattering at least, which is a nonlinearity that is presently a big issue for the continued scaling of fibers and lasers to higher and higher powers. That stimulated Brouin scattering is very much dependent on the photoelasticity. So if you can negate, if you can zero, or even if you can just reduce the photoelasticity, you can make great gains in pushing up the threshold at which things like SBS occur. And so in the case of that aluminosilicate fiber, we were able, just right out of the gate, it was the very, very first fiber to demonstrate, because of the high alumina content that we achieved by starting with something like sapphire, and then using the molten core process to get a much higher concentration of sapphire than you could ever get with a CVD process or conventional melt process. We were able to get about a 20 dB, almost 20 dB, which is almost a factor of 100 reduction in that SBS gain. So stunning improvements with actually very little effort in that sense. Alumina and silica, two of the most common materials that exist. Another good example is barium oxide and silica. So barium silicates, or barium oxide silica glasses, have been known for 70 years, but they also possess an immiscibility. So there is a limit, actually quite a small limit, to the amount of barium oxide that you can put into silica. If you stay on this theme of stimulated Brouin scattering and just use that as an example of a present problem that faces the continued scaling of light to higher powers and the application of light at higher powers, then barium oxide and silica is an interesting system because, as we just talked about, alumina has this negative photoelasticity, silica positive, so if you mix them you get a decrease for certain, and you may even get a zero. But the photoelasticity in barium oxide is actually about 10 times more negative, 10 times stronger, but in the same direction as sapphire or alumina. And so you need a lot less barium oxide to get to that 0 point. So in the case of the aluminosilicates, you need about 88 mole percent alumina, which is a lot. In the barium oxide silica system, you need only about 33 or 35% barium oxide. That's a much more tractable thing. So we did the same process. Barium oxide melts at maybe 1800 or thereabouts centigrade. We draw silica at about 1925, 1950 degrees centigrade. So again, molten core works great. Silica draws, barium oxide melts. Barium oxide dissolves in some of the silica glass. The resultant fiber, once cooled and core melt solidified, barium silicate with reasonably high concentration. Again, higher than you could get using conventional fiber and glass forming methods, of about, I think we maybe got about 20 or 25%. So we didn't quite get the highest percent we wanted, but nonetheless much higher than you otherwise could do. And we again see marked diminutions in that stimulated Brouin scattering. And so what one begins then to do and think about is go back to this thought about simplicity. right? The way that many people, again, are making fibers today, there we go, look like this. That's them, right? So they, again, go to great lengths at stacking preforms and drawing them into extraordinarily complicated fibers. Because they use the microstructure to influence the optical properties. The material, by and large, is all silica. So same material, but they use structure to influence properties. Our approach, though, is to use a new material and go to a much, 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 much simpler structure. So this looks just like a standard optical fiber, central core, homogeneous, large cladding, pure silica in that case, with a core that was derived from one of these molten core precursors. So this, in the cases of things like SBS, this, which is much, much simpler, has fewer unit operations to actually manufacture, tastes like, forgive the pun, silica, behaves like silica, does everything that silica does, but it outperforms something that looks like that. Right? So I would tend to favor making that any day over making that, especially when that has superior performance. Anyway, the paper is, as feature articles oftentimes are, provocative. It is meant to provoke, in some ways, maybe even insurrect this entire field of optical fiber, which I think has gotten old and boring, certainly from a materials perspective, and in some ways dusty. And so the provocation in here is for the material scientists to get back on the optical fiber wagon and assert their position, which is, as material scientists, we have the periodic table to bring to this game. So as demands continue to grow and new fibers are needed, or the performance of fibers need to match that demand, that the materials game is back on. It isn't just a structure where we're just going to live with silica, deal with silica, and influence the performance of the fiber by making it a very, very complicated structural thing. We are advocating for a return to a material solution, or a combination of materials and some structuring solution, because what we've been able to prove is that it is both simpler, both from a manufacturing perspective as well as from a materials perspective. It opens up the periodic table, and that's never a bad thing, always having more options. And it is a return to simplicity, which again is a benefit in and of itself. So enjoy the paper. Read the paper, contact us if you have questions, and in closing, I want to thank the Ceramic Society for letting us write up and publish that, and I want to thank particularly, there we go, the Joint Technology Office, who funded a lot of this work, both in my lab and Pete's lab over the years, the U.S. Army Research Office for their funding, and there we go, Northrop Grumman, who was an early but steadfast partner in the development of these fibers. So with that, I will thank them, and I will thank you.